calculations, but you are using the term spin adaptation. So could you please clarify the term?
Yes, spin adaptation means wave function is an eigenfunction of S square and MS operator. So that is what is called spin adaptation.
That is because SZ square and SZ and S square common. So they have
Yeah.
to have a common set of
Eigenfunctions. So you can common set of eigenfunctions. So if what we are saying that this is not a S square eigenfunction. This itself is not a S square eigenfunction. Neither is this an S square eigenfunction. But they are eigenfunction of the SZ operator. Okay. But now with the same MS values. So when I do a linear combination, MS value still remains the same, 0 in both cases. But now this combination becomes eigenfunction of S square operator. That is the new realization. Okay, I am not proving this, but I am just making a statement. This can be proved, it's not a problem.
So what you are saying is these are SU2 symmetric waveforms.
Yes.
And then this is a possible
Right.
basis for that.
But what is important to realize that the single determinant is not good enough if I want spin adaptation. So there itself, even without electron correlation, I have to often go beyond single determinant. The question that is generally asked, when is a single determinant spin adapted?
Can I refer
Yes.
Doesn't it amount to saying that the expectation value of the total spin in any of the spin adaptation is 0? You know,
Which
this spin, if it is SU2 symmetric, it shouldn't have
but depends on
net
single
magnetization.
If it is SZ, yeah, it is 0. These two are 0.
Yeah.
But I am talking S square.
That will have an expectation. But SZ
SZ is
will
0.
not have net magnetization.
No. Both
of
of
these
them have,
things will have
both of them MS is 0.
Yeah, exactly.
But that doesn't mean it's spin adapted. Unless it's an eigenfunction of S square. We are discussing eigenfunction of S square. Okay? So whenever I am saying spin adapted, please understand it is S square and SZ both. Simultaneous eigenfunction of both S square and SZ. So can I look at a single determinant? Now the next question. And say it is spin adapted or not. How do I say this? There is a very nice rule. Again, I will prove the rule. I will not prove the rule, I will just state the rule. And the rule itself is very interesting, that by looking at the determinant, I can tell if it is spin adapted or not. So I hope the two-electron part is clear. And the important part to realize that once I have been able to spin adapt, they are factorizable, as long as they are two electrons. And you have always an antisymmetric spin part, which is singlet, and a symmetric spin part, which is triplet. So triplets are associated with symmetric spin part. So even for the helium atom excited state, there are 4 terms. 3 of them are triplets, 1 of them is singlet, but they don't necessarily come from single determinant. There has to be mixing of 2 determinants to get those effective 4 terms. And you get a 1s1, 2s1 triplet, 1s1, 2s1 singlet. For 1s square, of course, there is no choice, so you have only singlet, so everything gets wrong automatically. And that's the Pauli principle that you know. So now let me change gear and say, how do I know which is singlet or which is being adapted for a general case, not even to electron case. Okay? So let us say that I just take the theorem without proving. Let's say that I have a determinant, a single determinant, has n spin orbitals. So SO is spin orbital. Every single determinant is characterized by n spin orbitals, right? If I know the spin orbital, the determinant is completely fixed. Of course, if I have n spin orbitals, it essentially means I have n electrons. That goes beside saying, and I can write n rows and n columns. Rows will be spin orbital, columns will be coordinates of the electron, which are basically space spin coordinates now. Space and spin. So a single determinant is completely characterized if I know n spin orbitals. Remember, the coordinates of the electrons are dummy. I call it normally 1, 2, 3, n. I can call anything. But the spin orbitals are important. They actually give the character of the single determinant. Then among these spin orbitals, some of them are alpha spin orbitals, some of them are beta spin orbitals. So let's make a very general thing. We can come back to this as an example. So let us say that I have n alpha spin orbitals, n beta spin orbitals. This is just a number such that n equal to n alpha plus n beta. I hope it's clear. Okay? So you have total number of spin orbitals is n, out of which n subscript alpha are the number of spin orbitals we have alpha spin, n beta are the number of spin orbitals with the beta spin, and the total is of course equal to that. So for example, if you take an example here, this determinant, my n equal to 2, how many alpha spins are there? 1. How many beta spins are there? 1. Both of them are 1. Okay? And the same thing there. N equal to 2, n alpha equal to 1, n beta equal to 1. On the other hand, if I take the other two, for example, I write cryptically 1s alpha, 2s alpha. That's a determinant. I can make it a determinant. N equal to 2, but now your n alpha is 2, n beta is 0. Correct? Because there is no beta electron, or vice versa. N beta equal to 2, n alpha equal to 0. So just remember this for the context that when I am doing this. Each of the n alpha and n beta spin orbitals has also a space part, associated space part, right, which we are not discussing. So n alpha has a space part, all these n alpha spin orbitals have a space part. Of course, all these space parts are multiplied by alpha spin. That is understood because they are alpha spin orbitals by definition. Just remember this. So n alpha has some space part, n beta has some space part. Okay, into beta. N beta number of space parts. Now let's assume n alpha is greater than equal to n beta. Okay, it can be equal or greater. So one of them is larger. So let's assume that the n alpha is greater than equal to n beta. Then the theorem says if the space part of the smaller one, which is n beta spin orbital, is a complete subset, which means essentially the entire space part is submerged, is complete subset of the space part of the n alpha spin orbitals, then the determinant is spin orbital. I will explain this. So n alpha is greater than or equal to n beta. So n beta has some space part. Those space parts should be completely contained by the space parts of the n alpha, which is the larger set. I hope you understand. This should be a complete subset of the larger one. Now we look at it. Then it is spin orbital. Now we look at this. N alpha equal to 2, n beta equal to 0. The first case. There is nothing there for n beta. So anything that happens is spin orbital. I don't have to bother. Alright? Same thing happens for 0, 2. Look at this now. You have 1 and 1, so it's an equal. Now it doesn't matter. If it is equal, then at least the space part of this must be equal to the space part of this, which is not. The space part of alpha is 1s, the space part of beta is 2s, and that's the problem. Okay, and the same goes for here. On the other hand, if you look at the ground state, which is just 1s alpha, 1s beta, this is a short form of writing determinant. Just write the spin orbital. Now you look at this. In n equal to 2, n alpha is 1, n beta is 1, but now the beta part and the alpha part have the same space form. So there is no problem. I will actually generalize this to higher electron determinants, but this is a very useful rule. And not many quantum chemistry textbooks actually even state this properly. There's one book called Hurley, S.E. Hurley. It's very fun, very good book actually. The theorem is proved. So, but I'm just stating the theorem again. So, if a single determinant has total n spin orbitals, out of which n alpha or alpha, n beta is beta, such that the total n is of course n alpha plus n beta, then n alpha spin orbitals will have some space part into alpha. N beta will have some spin part which is beta. Assume that n beta is smaller or equal to the n alpha. In that case, if the complete, all the space parts of the lower one is contained in the space parts of the higher one, then it is spin orbital. What is the spin? I will come to that. Otherwise it is not. So look at the determinant. You should be able to find this immediately. That n beta is 1, n alpha is 1. So the space part of beta must be the same as space part of the alpha, which it is not. Hence it is not a spin adapter. Again, remember this is only true for a single determinant. So a combination of two such wrong determinants gives you spin adapted function, however. So the theorem is only for a single determinant. That is very important. Is it clear? The theorem statement of the theorem, is it clear? We are not proving it, just the statement. Let me now go to a higher electron determinants and try to show this. And this is something that in chemistry we always do that, but we have never realized what it is. So let's look at a picture where, so I have, let's say 4 electrons like this, and another 2 electrons here, with both upspin. Now, if you look at it, it's clearly spin adapted. You have 6 electrons, right? 6 spin orbitals. 4 of them upspin, 2 of them downspin. The downspin is lower. The space part of the downspins are completely contained in the upspin. Correct? Because they have the same space part. So it is spin adapted. On the other hand, just turn this around here. This is not spin adapted. Immediately. And you can go ahead with larger and larger numbers. You can have higher problems like this. So if you want three parallel spins, then this has to be like this, if they are different space orbitals. Okay? So of course, if this is spin adapted, and it is very clear that your S is now related. That's a quartet state. That we already know, that whenever alpha. So in a very simple way to do is the following, is that if you can identify a doubly occupied core, so that's another way of stating this theorem. In a single determinant, if you can identify a doubly occupied core, that means set of orbitals which are doubly occupied, then the rest of the electrons must have parallel spin. Otherwise you are in trouble. And then of course it's very easy by looking at those remaining electrons to predict their spin. And that is something that we always do. In fact, if I have given you this determinant, a structure, you would immediately say it's a quartet state, right? Without the blinking of an eye. But I'm trying to prove it from a determinant theory. When I write it, the moment I change one of them, it's not. And then I have to bring in other determinants, make linear combination, and eventually make a spin adapted function, which is possible to do, as I told you. However, since it's a larger electron system, it cannot be factorized. That's a different one. But at least you can make spin adapted. Okay, for 2 electron, I said it is factorized. So this is a very interesting part of the problem. And then you have special situations like 1s squared, 2s squared, and a degenerate 2p, let's say. And I have 2 electrons. Of course, you already know the answer. You will put them here and here, and then you will say it's a carbon atom. Of course, it's a triplet. By my definition, now we know it's a triplet because the upspins are occupying different space. If I, of course, make them here, now it will be singlet because they are still occupying same space. If I do this, then it is no longer spin adapted. So you just play around and very, very easily give an answer. So the energy is not an issue here. Which is higher, which is ground state, which is excited state, I am not discussing. If you want to discuss that, then I have to compare the energies of this vis-a-vis energy of, let's say, 1 up, 1 down. Both are spin adapted. And then this next question is, which is lower in energy? Of course, you already know the answer. That's the Hund's rule. I'm going to simply prove the Hund's rule. So to do that, there is a very important theorem, and that was actually again proved by John C. Slater. And it's actually not even a theorem, it is called Slater rules. These allow you to calculate the matrix element of the Hamiltonian with respect to its determinant. So now let me write the determinant once again in a very general form. Chi1, chi2 to chi n. Yes?
Can we say this that when the Hamiltonian, if you say that it is spin adaptive wave function, then the effective Hamiltonian which describes them has to be of the form S1 dot S2, S2 dot S3, S3 dot S4, which are all rotationally symmetric. It has to be, right?
But yeah, but our Hamiltonian does not have explicitly spin. We don't have spin. It's a non-relativistic Hamiltonian. We don't have any spin in the Hamiltonian. We are only talking of the spin adaptation of the wave function. That is the wave function and eigenstates of S square and S. That is all we are discussing.
Which it would be if they are all S1 dot S2, Si dot Sj, as many electrons as you put. If it is of this form, it's ensured.
Yeah, of course. That's a different. But our Hamiltonian doesn't have spin explicitly. Okay, it doesn't. It just have a 1 electron energy and a 2 electron Coulomb repulse. So they are all function of R. I don't have that explanation.
That is what I was saying. Coulomb, if you have Coulomb structure, then let's say you take the states what you have, basic states, and you form a Hamiltonian. If you diagonalize it, you will end up with these states.
Yes, of course.
And then in that diagonalized Hamiltonian, the effective Hamiltonian will be of S1 dot S2.
Yes, that's right. But that is the procedure to obtain.
Yeah.
Explicitly, the Hamiltonian doesn't have. Okay, that's the procedure.
This will emerge.
Yeah, this will emerge from the effective Hamiltonian. But our physical Hamiltonian doesn't have any spin. Okay, so what we want to do is that, let's say these are my n spin orbitals. So they can be any spin now. Depending on what are the spins and what are the space parts, I will declare whether it is spin adapted or not a spin adapted. So that is something I am not discussing. What we are now doing is to find out, and this is what Slater gave, how do I calculate this complicated integral? So this is very often required for calculation of energy. So how do I simplify this? To do this, first let us identify, look at the Hamiltonian once again. So our Hamiltonian, either for atom or for molecules, under Born-Oppenheimer approximation for molecule, can be written electronic Hamiltonian as a 1 electron part and a 2 electron part. Without any loss of generality, we can write a 1 electron part. 1 electron part contains kinetic energy, attractions of all kinds, electrons with all nuclei, single nuclei, multinuclei, whatever. If there is electric field, everything goes into 1 electron part. So in general, I have a 1 electron part and I have a 2 electron part. So if you remember, so this is I equal to 1 to n. This is I less than j, 1 by Rij. The n is the number of electrons in this case. It's not the spin orbitals because they are now referring to the coordinates. So they are number of electrons in the Hamiltonian. So if I write this determinant, the Slater wrote a very simple form. Write this as a sum over I, chi I, h, chi I. Where I is now the spin orbital index. I is the spin orbital index. The coordinate is of course dummy because I am integrating, it's a 1 electron integral. Remember h is a 1 electron operator, so I am just integrating. Chi I star 1, h of 1, chi I 1, chi I star 2, h of 2, chi I 2, whatever. It's a dummy variable. It's a complete definite integral. Plus half of sum over I and j. Again, these I and j's are now spin orbital, chi I chi j, 2 electron integral, antisymmetry, chi I chi j. I will explain what this is. The chi I chi j, antisymmetric chi I chi j, is nothing but chi I 1 chi j 2, 1 by R1 2, chi I 1 chi j 2, minus chi I 1 chi j 2. This is very important. This minus part, 1 by R1 2, chi j 1. So this is called the exchange integral, the second part. So this is of course antisymmetric, because if you interchange 1 and 2, because of this minus sign, the entire integral is antisymmetric. If I interchange the coordinates 1 and 2, it becomes negative on one side, not on both sides. So if I interchange on one side I and j, you can see that they change sign because of this negative sign. So that is the reason it is called antisymmetric two-electron integral. With that, this letter gave a very simple formula. Just write this out. For any determinant having n spin orbitals, you can simply write down the recipe. Again, the proof is not important. Write down the form as it exists. And you can see that a very complicated foreign dimensional integration, because of the space and spin, has been simplified to n 4-dimensional. Okay? And another NC2 8-dimensional integral.
I think the 1 and 2 will be reversed, otherwise they are the same.
Huh?
1 and 2 in the second.
Yeah, second one. No, I wrote Chi J1. No? Sorry, the J and I are not
Oh,
seen.
J, okay.
I wrote Chi J1. Of course, they are reversed. It's exchange. So Chi I1, Chi J2, 1 by R1 to Chi J1, Chi J2. Okay? So you can see the simplification. A foreign dimensional integral has been now simplified. Very often, it is called 1 and 2 electron integral. In the quantum chemistry jargon, 1 electron is 4 dimensional, 2 electron is 8 dimensional, including spin. Very often, the spins are trivially integrated because the Hamiltonian does not contain spin. So spin integration is actually trivial. What is really non-trivial is the integration over the space parts of the problem. And that is what we will actually show now. That what happens if I have an wave function which has alpha alpha vis-a-vis alpha beta. Why is it that the alpha alpha is preferable than the alpha beta? That's the Hund's rule. So it's a demonstration of the Hund's rule. And all of you, of course, know it because of exchange stabilization. So that is what you say. So I just want to show from this rigorous formula how does exchange stabilization appear. That because of the exchange, there will be a stabilization. So if I do take a system like helium atom or hydrogen molecule, where this is a molecular orbital, let's work it out. So of course, this is nothing but 1s alpha, chi 2 is nothing but 1s beta. If I work it out, it's very easy to show that the energy will be first the two space part energy, because the spins are trivially integrated. Alpha alpha is 1, beta beta is 1. So this summation over 1 to 2, each of them will give the same results, and I can actually write this as 2h of 1. This is, let's say, 1. 1 is essentially 1s in this case. I'm not writing 1s explicitly. Then if I write here, I now have several terms. I can be 1 to 2, j can be 1 to 2. It can be 1s alpha, 1s alpha, 1s alpha, 1s alpha, 1s beta, 1s beta, or any combination, 4 combinations. With a factor half. With a factor half, yes. If you do this, then